Hello students, we're going to be looking at the micro world where we are visualizing things as atoms and molecules, and how is that converted to the macro world with grams, like quantity we can see. So to go back to the start with the atom, the atomic mass, which is the mass of an atom, is normally measured using the atomic mass unit. So by definition, we decided that one atom of carbon-12 does weigh 12 atomic mass unit, and use this as a standard to know what other atoms weigh in comparison. So for example, one hydrogen atom turns out to be 1.008 atomic mass unit on average. Now let's understand what I meant by average, the average atomic mass. So the average mass, the reason why we call it average, because it's averaging all naturally occurring isotopes. What does that mean? Here is an example. Almost every element in nature will exist in multiple isotopes. So natural lithium, just the way it does exist naturally, you will have 7.42% of lithium as lithium-6, weighing 6.015 atomic mass unit, and 92.58% of it as lithium-7, weighing 7.016 atomic mass unit. So in a nutshell, that means that every time you are looking at 100 atoms of lithium in nature, almost 93 of them will be lithium-7, and 7 of those atoms will be lithium-6. This is one way to look at it. So if you are to view lithium in the periodic table, then you will find that it is reported at 6.941. So where does this number come from, right? I mean, think about it. This number is closer to 7 than it is closer to 6. And it does make sense because most of lithium occurs as lithium-7, not lithium-6. If you want to know how we can get this number, this is the math you use. So you take the percentage of lithium-6, which is 7.42 over 100, and you multiply it with the mass, which is 6.015. Then to that you add the percentage here, which is 92.58 over 100, and you multiply that by the 7.016. When you perform the math using your calculator, you will find that the calculator will say 6.9417258. So in a nutshell, this is where this number is coming from. It's coming from the fact that I am averaging all the different atom isotopes based on their abundance. So every time I count for a mass, I take into account what is the percentage of that specific isotope. Now for compounds, we use, this is if we're looking at one atom, this is how we average the atomic mass. When we look at molecules, now remember, molecules are made of more than one atom, and if they are covalently bonded, like sulfur dioxide in this example here, well, the molecule is made of one oxygen atom, and one sulfur atom and 2 oxygen atoms. So you take one sulfur atom and you find that it has a atomic mass of 32.07 atomic mass unit. You have 2 atoms of oxygen, 2 times 16.00 atomic mass unit. You add them up together, and that will be here the molecular atomic mass for sulfur dioxide, which is 64.07 atomic mass unit. The formula mass for a formula unit, and this is the term we use when we have an ionic compound. If it's a covalent compound, we say molecule, but if it's an ionic compound, we call it a formula unit. So now, can you have the periodic table? Because again, a reminder, these numbers are the numbers that you will find underneath the element in the periodic table. Now, using your periodic table, I would like you to take some time and calculate the molecular mass of methanol, CH4O, and the molecular mass of caffeine. All right. When it comes to chemistry quantity, in general, in life, we use a quantity that works for us. For example, anytime we have 2 of something, we call it a pair. Anytime I say the word pair, you do understand that I am talking about 2 of whatever I am referring to. When I say a dozen of anything, it means 12 of that thing. So this will work great in our everyday life or in our macro world, but in our micro world, I can't take you to the lab and ask you, oh, can you please weigh 12 atoms of copper? That is not possible. That quantity is too small to work for us. It cannot be seen by your own eyes or it cannot be handled. So therefore, the quantity that will work for us in chemistry has to be a very large quantity to be practical. And this is the mole. So a mole defined as it contained as many particles, which can be atoms, molecules, as the number of atoms in exactly 12 grams of carbon-12. Meaning, if I took 12 grams of carbon-12, that sample will have a certain amount of atoms that equals 1 mole. That amount is what is defined as Avogadro's number, and it is 6.022 times 10 to the power 23 particles. So this is what we define a mole as. 1 mole of anything contains 6.022 times 10 to the power 23 of that specific thing. Now, please make sure this is here a number that you do need to memorize. This is a number that you will be using so frequently in chemistry. All right, so Avogadro's number, which is the number of particles in any mole. Here is a picture. So what do these samples have in common? This is a sample of carbon, a sample of sulfur, mercury, copper, and iron. What they have in common that this is here, each one of them contains 1 mole, which means this here has 1 mole of carbon. This is 1 mole of sulfur. This is 1 mole of iron, 1 mole of mercury, 1 mole of copper. So what does that mean? It means that this here has 6.022 times 10 to the power 23 sulfur atoms. And this sample of nails has 6.022 times 10 to the power 23 iron atoms, and so on. Now, what do they have in common is number of particles, but would they weigh the same? The answer is absolutely not. Why? Because every atom does have a different mass. So that number of sulfur is not going to weigh the same as that number of atoms of iron. Now, if you look at the average atomic mass, you will find that mercury is the heaviest, so that sample will be the heaviest accordingly. Carbon is the lightest, and that sample will have the smallest mass accordingly. Now, molar mass or the molecular weight is the mass of 1 mole of eggs, atoms, molecules, ions in grams. So molar means per mole. So when I say molar anything, it means per 1 mole. So molar mass meaning mass of 1 mole. Now for any element, molecule, or formula unit, the atomic or molecular or formula mass is equal to the molar mass in grams. So whatever numbers we did take previously from the periodic table, we just gonna express them with grams to become molar mass. So remember sulfur dioxide? We did decide that one molecule has 64.07 atomic mass unit. If I want to know the molar mass, which is the mass of a mole of those molecules, then it will be that number, but in grams, which will be 64.07 grams. Now, a mole of one molecule of water will have the 18.0 atomic mass unit. However, 1 mole of water will have 18.0 grams, and that will be what we call the molar mass of water. Now, how can we utilize the molar mass as a conversion factor? We can always take moles to mass and vice versa, mass to mole. All what we need to do is to use the right conversion factor, which is the molar mass conversion factor. Here is an example. Let's solve this together. How many moles of sodium are in 3.45 grams of sodium? What you do here, you start with 3.45 grams of sodium. Then you go to the periodic table and you look up the atomic mass of sodium and you say, okay, 1 mole of sodium does weigh 22.99 grams. I always have these questions from the student. How many sig figs should I get when I look at the periodic table? My answer is at least 4. So now when you do the math, you're going to log all these numbers in. You log in the numbers into your calculators and the answer will be, remember you have to have 3 sig fig, 0.150 mole, because this measurement here has 3 sig fig, which will determine how many significant figures I can have. Now, calculate the mass of 1.6 moles of water molecules. Now I'm going to approach this differently. I'm going to start with 1.60 mole of water. And I want to convert that into grams. So I'm going to use the molar mass conversion. I'm going to say, okay, I need mole of water down here. And every mole of water will weigh 18.00 grams. So now you log in these numbers into your calculator. And the answer will be, having 3 sig fig again, 28.8 grams of water. So as you can see in the first example, I took grams and converted them to moles. In the second example, I took moles and converted them into grams every time I'm using the molar mass conversion factor. Using Avogadro's number as a conversion factor, so if you go from moles to particles and vice versa, particles to moles, you will need the Avogadro's number conversion factor. Let's look at an example. How many sodium atoms are present in a 35.2 mole sample? One more time. What we do, we're going to start with 35.2 mole of sodium, and I'm going to convert that in a conversion factor into number of atoms. I'm going to say there are 6.022 times 10 to the power 23 sodium atoms for every 1 mole of sodium atoms. Plug this number into your calculator and the answer will be 2.1236 fig times 10 to the power 25 sodium atoms. All right. Practice using chemical formulas as conversion factor. Let's see, what does that mean? How many moles of oxygen are there in 18 moles of carbon dioxide? So mole again is a quantity. So let me explain what does that mean to me. Every carbon dioxide molecule has 1 carbon atoms and 2 oxygen atoms, right? So when I use mole, it's just a quantity. I am multiplying everything by Avogadro's number. So if I said a molecule has 1 carbon atoms and 2 oxygen atoms, then I can also say a mole of carbon dioxide does have 1 mole of carbon atoms and 2 moles of oxygen atoms, right? It's the same ratio. It comes from the formula. So therefore, we can use conversion factors. So if they're asking how many moles of oxygen atoms are there, I'm going to start with 18 moles of carbon dioxide, and I'm going to say there are 2 moles of oxygen atoms for every 1 mole of carbon dioxide. This cancels out. The answer will be, of course, this is exact. So this is here my sig fig determination will be 36 moles of oxygen atoms. How many moles of oxygen is, as I said here, they are trying to show you the conversion factors. So for example, here in calcium carbonate, the ratio will be slightly different because here I have 3 moles of oxygen for every mole of calcium carbonate. Now let's do the following question. How many glucose molecules, C6H12O6 is a glucose molecule, are present in 0.225 mole sample? And then there is a follow-up question. How many carbon atoms are present? So let's take it one question at a time. If I have 0.225 moles of glucose, and I will convert that into molecules. So what I'm going to say, I'll say, okay, every mole of glucose does have 6.022 times 10 to the power 23 mole of glucose. Now, when you do the math, the answer will be taking into account the correct number of sig fig. 1.35 times 10 to the power 23 molecules, sorry, this is here is not mole, guys, molecules of glucose, right? That does answer the first question here. Now the second question, how many carbon atoms are present? Well, this is number of molecules. So what I can say immediately with a follow-up conversion factor, there are 6 carbon atoms for every 1 molecule of glucose. So molecule cancel molecule, and if I multiply this answer by 6, then the answer will be 8.13 times 10 to the power 23 carbon atoms. So in summary, 1 mole of 2 different substances will contain the same number of particles but different masses. A mass can be converted to mole using the molar mass conversion. Mole can be converted to particles using Avogadro's number. So let's see if we understand molar mass conversion. Let's have a question. How many atoms are there in 0.551 gram of potassium? Before I solve this question, I would like to take you back for a second to see this picture, and I want to highlight something special for you here. So this here is what I would like to highlight, guys, for you. The mole is in the middle of all of what I do, right? Mole is the core of my calculation. So what does that mean to me? It means that if I want to go from mass to particles or particles to mass, in the middle, the core that will take me will be moles. So I always tell my students, moles are the core of our calculation. Anytime you need something, you have to, because if you know the moles, you can know particles. If you know the moles, you can know the mass. So let's see how we can address the next question. Now, how many atoms are in 0.551 gram of potassium? So what we will do, we will start by saying there is 0.551 grams of potassium. I'm going to have to convert that into mole. So I'm going to have to say 1 mole of potassium has the atomic mass 39.10 mole of potassium. So now I got, so that's not a mole. I am sorry for that. That's meant to be gram of potassium. Okay, so now grams of potassium cancel out and I have moles. If I have moles, can I take them to number of atoms? Of course, by using Avogadro's number. I will say there are 6.022 times 10 to the power 23 potassium atoms for every 1 mole of potassium. You perform this math, taking into account your answer needs to be presented in 3 sig fig, and the calculator here will say that you have 8.49 times 10 to the power 21 potassium atoms. All right, let's see what's next. What is the mass of 1.3 times 10 to the power 23 formula units of sodium chloride? Let's see how we're going to address that. We're going to start with, remember we say formula units because it's an ionic compound. It is like you're saying molecule, but for ionic compounds you have to say formula units. So what we will say, there are 1.3 times 10 to the power 23 sodium chloride formula units, and now we're going to convert that into moles. So we're going to say 1 mole of sodium chloride formula unit does have 6.022 times 10 to the power 23 formula units of sodium chloride. Now I'm going to convert that into grams, so I'm going to have to calculate the molar mass of sodium chloride, which is 58.44 grams of sodium chloride for every 1 mole of sodium chloride. Now you do the math using your calculator. The answer will be 12.62 grams of sodium chloride. Let's see the next question. How many hydrogen atoms are in 72.5 grams of isopropanol? So we start the question by saying we have 72.5 grams of isopropanol. We're gonna have to convert that into mole. So 1 mole of isopropanol, then you calculate the molar mass of isopropanol, which is 60.1 gram of isopropanol. So now that you have moles of isopropanols, can you calculate number of hydrogen atoms? So what you're gonna say, okay, I know that there are 8 moles of hydrogen atoms for every 1 mole of isopropanol. That came from the formula. So now this canceled out. Moles of isopropanol cancel out. You have moles of hydrogen atoms. And if you have moles of hydrogen atoms, can you calculate number of hydrogen atoms? Yes, using Avogadro's number. So you're going to say there are 6.022 times 10 to the power 23 hydrogen atom for every 1 mole of hydrogen atom. Now you go through your calculator. In this case, you do have to have 3 sig fig. And the answer will be 5.81 times 10 to the power 24 hydrogen atoms. That does conclude our topic here, and I will see you in the next lecture.